Hello, my name is Jeff Richley. Today I'll be presenting my project titled Learning-Based Configuration Space Goodness Fields, which explores how learned surrogate models can be integrated directly into the motion planning process. This work was done in the context of planning and control in autonomous and robotic systems at Old Dominion University, and it extends classical planning approaches such as sampling based planners by replacing repeated collision checking with learned models of configuration space feasibility. While the project goes beyond traditional examples like A star or RRT, the focus is still very much on planning behavior, planning efficiency, and how control relevant decisions can be guided by surrogate representations of the environment. The core motivation for this work comes from a well known bottleneck in motion planning, the collision checking. In many classical and sampling based planners, collision checking can account for roughly 80 to 90% of the total computation time. That means most of the planner's effort is not actually spent reasoning about paths or control decisions, but repeatedly asking a very expensive yes or no question: is this configuration in collision? The challenge is that configuration space boundaries are inherently sharp and discontinuous. Small changes in configuration can abruptly switch a state from feasible to infeasible, which makes these boundaries costly to evaluate and difficult to model directly. What you're seeing on the right is an example of a learned goodness field generated using a Gaussian process model. The colored field represents a continuous estimate of collision likelihood across configuration space, while the red outline shows the true collision boundary obtained from exact collision checking. From a planning and control perspective, this kind of representation is powerful because it gives the planner dense, smooth information about feasibility without requiring an oracle collision check at every query. The goal is not to replace classical planning algorithms, but to accelerate them by allowing sampling, pruning, and control relevant decisions to be guided by learned surrogate models instead of a repeated geometric evaluation. To understand why surrogate models are useful, it helps to briefly revisit the idea of configuration space. The configuration space, or C space, represents all possible configurations of a robot. In this example, we're looking at a simple 2 degree of freedom system, so each configuration can be described by two joint angles. In the image on the right, the horizontal axis corresponds to the first joint angle, or theta 1, and the vertical axis corresponds to the second joint angle, or theta 2. Each point in that space represents a unique pose of the robot in that workspace. Each configuration is classified as either collision-free or in collision, based on whether that pose causes the robot to intersect an obstacle. What makes planning difficult is the boundary between these regions, which is highly nonlinear and often discontinuous. As shown here, relatively simple obstacles in the physical workspace can produce complex, fragmented regions in configuration space. From a planning and control standpoint, accurately capturing this structure is critical because planners rely on it to decide where to sample, how to move, and which motions are feasible. At this point, I want to define what I mean by a goodness field, because this is a term I use throughout the rest of the talk. A goodness field is a continuous surrogate representation defined over configuration space. For each configuration, it assigns a scalar value that represents feasibility, where higher values indicate collision-free configurations and lower values indicate configurations that are in collision or near collision. The red curve shows the true collision boundary obtained from exact collision checking. Dark blue regions correspond to areas where the goodness field is very confident that the configurations are in collision, while green regions indicate areas where the model is confident the configurations are safe. Rather than treating feasibility as a hard binary decision, the goodness field provides a smooth transition across the boundary, capturing how close a configuration is to collision. From a planning and control perspective, this is valuable because it gives the planner dense, continuous information about feasibility. The planner can use this field to guide sampling, prune unsafe regions, and shape heuristics, while significantly reducing the number of expensive geometric collision checks. This slide compares the three surrogate modeling approaches evaluated in this work: fast Fourier transform-based surrogates, Gaussian processes, and radial basis function interpolation. All three are trained on the same set of sampled collision labels and evaluated over the same configuration space. Starting on the left, the FFT-based surrogate is extremely fast to compute and evaluate. It operates by smoothing collision information globally in the frequency domain. However, that global smoothing causes sharp, free obstacle boundaries to become blurred. You can see this in the visualization where the transition across the red ground truth boundary is spread over a wider region, which can cause narrow passages to be poorly represented. In the center is the Gaussian process surrogate. The Gaussian process provides the highest fidelity representation of the boundary, closely tracking the true collision contour. Because it is a locally adaptive, non-parametric model, it is able to preserve sharp transitions while still producing a smooth field. An additional advantage is that the Gaussian process naturally provides uncertainty estimates, which can be used to guide adaptive sampling and refinement. On the right is the radial basis function surrogate. Radial basis function interpolation also produces a smooth, continuous field and does not require a structured grid. Its accuracy is competitive with the Gaussian process, particularly away from sharp boundaries, but it tends to slightly smooth narrow features and does not provide uncertainty in the same principled way. From a planning perspective, these differences really matter. Boundary blurring can reduce planner performance in narrow passages, while higher fidelity surrogates preserve the structure needed for reliable sampling, pruning, and path generation. This slide looks at surrogate accuracy from a quantitative standpoint, focusing on how performance evolves as more collision samples are added. Rather than the absolute values, the important takeaway here is how efficiently each model learns the collision boundary. What stands out is the Gaussian process achieves strong performance even at relatively low sample counts, and then improves steadily as more data becomes available. This suggests that the Gaussian process is both sample efficient and well suited for capturing localized structure near the boundary. The radial basis function surrogate follows a similar trend but plateaus earlier. While it benefits from additional data, its improvements is more gradual, indicating that it smooths over fine boundary details even as sampling density increases. The FFT-based surrogate shows the weakest learning behavior because it enforces global smoothness. Adding more samples yields diminishing returns, and the model struggles to sharpen the boundary regardless of data volume. From a planning perspective, this means that higher fidelity surrogates not only produce better fields, but do so with fewer samples, which directly impacts how quickly a planner can build reliable representation of feasibility. After establishing baseline surrogate performance, we evaluated several refinement strategies aimed at improving boundary accuracy by selectively adding new samples. Specifically, we tested gradient-based refinement, curvature-based refinement, uncertainty-driven sampling using the Gaussian process variants, and Poisson boundary sampling. While these methods differ in how they identify candidate points, they all share the same goal: concentrating samples near the collision boundary where accuracy matters the most. The image on the right shows an example of this process. The sampled points clustered tightly along the estimated boundary, illustrating how refinement focuses computational effort where the surrogate is most uncertain or changing rapidly. Interestingly, despite their conceptual differences, all refinement strategies tend to concentrate samples along very similar boundary regions. In this 2 degree of freedom setting, the resulting improvements in surrogate accuracy were relatively small. The key takeaway is that the initial sampling quality mattered far more than the specific refinement strategy used. Once the boundary was reasonably well covered, additional refinement provided diminishing returns. This suggests that, at least in low dimensional settings, careful initial sampling is more impactful than sophisticated refinement schemes. Up to this point, I focused on how well the surrogate models represent configuration space. The natural question is whether that representation actually improves planning performance. To answer that, we integrated the Gaussian process goodness field into several classical planners and evaluated their behavior using standard planning metrics. The plots here summarize success rate, mean path length, and minimum clearance. Across all planners, success rates remain high, between roughly 93 and 98%, indicating that the surrogate does not degrade planner reliability. At the same time, mean path lengths were very consistent, around 2.9, and the clearance values remained stable across planners. It shows that the surrogate guided planners produce paths that are comparable in quality and safety to those generated using exact collision checking. The key takeaway is that goodness fields change how the planner reasons about feasibility without changing what the planner ultimately produces. We gain computational efficiency while preserving the planning behavior and control relevant properties that these algorithms are designed to deliver. To close, I want to summarize the key insights from this work. First, Gaussian processes consistently provide the most accurate and stable surrogate representation of configuration space boundaries. They preserve sharp transitions, learn efficiently from limited data, and integrate naturally into the planning process. Second, FFT-based surrogates tend to blur narrow passages due to global smoothing. While they are computationally fast, this loss of boundary fidelity directly impacts accuracy and ultimately planning reliability. Finally, in this 2 degree of freedom setting, the choice of surrogate model mattered far more than the choice of refinement strategy. Once the boundary was reasonably sampled, additional refinement produced diminishing returns. Taken together, these results suggest that careful surrogate selection is a critical design decision when integrating learning into motion planning and control. To close, I want to show a short demonstration of the planner operating with a Gaussian process goodness field integrated into the planning loop. On the left side of the video, you see the robot operating in the workspace. The path shown on the top is the raw path produced directly by the planner, while the path on the bottom has undergone a simple string pulling post-processing step, resulting in a smoother trajectory with reduced jerk. On the right side, you can see the corresponding configuration space representation used during planning. The grid overlay shows the discretization used by the A-star planner, and that grid is derived from the Gaussian process goodness field surrogate. Instead of relying on exact collision checks at every grid cell, the planner queries the learned goodness field to estimate feasibility and guide the search. This allows the planner to reason efficiently about safe regions of configuration space while preserving the structure needed for reliable path generation. Overall, this demo illustrates how learned surrogate models can be embedded directly into classical planning and control pipelines, improving efficiency while maintaining smooth, stable, and interpretable planning behavior.